This is Mr. Maxwell for Pingree AP Biology. Today we're going to talk about evolution, microevolution in particular, and that is evolution that happens below the species level. And so there are a couple of things you should have already learned about Hardy-Weinberg equilibrium, which describes a non-evolving population, and you should know that the criteria for that are you have to have an infinite population size, you have to have non-random, or you have to have random mating, you have to have no natural selection, you have to have no net mutation, and no immigration or emigration. And we're going to address each of those today. First one is infinite population size. As you can see in the graph, if you have infinite population size, the frequency of a particular allele doesn't change. And notice that we're only here looking at the frequency of allele A1. Allele A2 is going to have exactly the opposite of A1. So if it's 0.5 for allele A1, it's obviously 0.5 for allele A2. So they're only going to show them one. And then here you'll see the genotype frequencies. So here's homozygous, here's the heterozygote, then here's the other homozygote. So if we start out with a much smaller population, say 100, and we start the population with 0.5 for A1 and 0.5 for A2, you'll notice that sometimes one allele goes to fixation. In other words, it goes all the way up to 1. And if A1 goes to 1, A2 must go to 0, which is called extinction. So over time, you get, with a small population size, you get alleles going to either fixation or extinction. And infrequently, you'll get them by random chance sticking around in the middle here, but notice how how jagged the peaks are here. There's lots of fluctuation. And the reason for that is due to a thing called sampling error. Because you have such a small population size, each individual represents a larger portion of the whole. And so if you think about it, if you flip a coin, you can get a coin to come up heads a fairly large number of times. And if you flip that coin 100 times, you're going to get some rare events. That's maybe not as clear of an explanation as I'd like. Maybe I'll go back and delete that. But basically, because each individual is a larger portion of the whole, random events have a bigger effect. Whereas if your population is, let's say, 20 billion, each individual is such a small amount that the wiggle in here is very, very small. And so there are two situations which are both due to genetic drift. One of them is called founder effect, where you take a sample, you have an original population, and then you take a sample from that population. For example, when I talk about this in class, we look around the class and say, are you guys representative of the population in New Jersey? And of course, you're not. Lots of different gene frequencies in there. And if you take that small population and move it to a different area, let's say you crash on a desert island and the class has to, nobody's going to get you, so you do the old Lord of the Flies thing and set up your own population. Your population is not going to look entirely like the original population because you started with so few people. Real life examples of this, the Amish, basically there were about 200 people who founded the Amish population in eastern Pennsylvania, and one family, there was basically one family that had polydactyly, 6 fingers on one hand, and today that persists. There's a large proportion of the Amish have 6 fingers on one hand, and it's a matter of founder effect. So that allele was present just by random chance at high copy number. And inbreeding, remember that inbreeding does not create mutations. All it does is makes it more likely that a particular mutation is going to be present in the homozygous form. In other words, more likely you're going to get 2 copies of it because you married your cousin. Okay. Now, bottleneck is basically the same fundamental mechanism, but rather than having a population sampling from a population and then going and founding a new population, what you have is a population that gets reduced down to a few individuals. So the example given here is seal hunting, and the original population had a lot of variety, hunted down so that there was a very, just by random chance, a very small amount of variety. And then when that population is allowed to expand, then the original alleles are no longer present. One real life example of this is cheetahs. If you look at the average heterozygosity in cheetahs, you'll find that they are nearly clonal species, and this is probably because of a bottleneck caused by the feline immunodeficiency virus. Okay, so to review, genetic drift is due to sampling error, which is that small sample size is not necessarily going to reflect the larger population. Two instances or sampling error is what causes it. We talked about founder effect, we talked about bottleneck, and in small populations, usually one allele becomes fixed, it goes to 100%, and the other goes extinct. That's what you need to know about genetic drift. Okay, immigration and emigration is pretty simple. Immigration is when things come in to a population. Emigration is when things leave. So, in immigration, you're adding alleles to a population, and in emigration, whenever somebody leaves, they take their alleles with them. So here we have, a goose, I guess, or a swan or something, taking his little a's away from this population, giving them to this population. Of course, that's going to change things. In allele A1, if you run some simulations, you can see that without immigration in a small population, you get this fixation or extinction happening. But if you allow immigration from a population, from another population, this can lead to more stable populations. So one of the things that conservation biologists try to do is connect small populations so that if a particular allele goes extinct in a particular population, that a neighboring population can resupply that population with that allele, so it doesn't go extinct globally. Because diversity is really important, to maintain populations. Okay, so what's a mutation? I like this picture because it, the popular idea, the Hollywood idea of what a mutation is, kind of fuels the misunderstanding, I think, that people have about what mutations are. Mutations are much smaller usually than always, than creating superhuman turtles out of turtles, but mutations are the only source of new alleles for a species, and unless you're going to do hybridization of species, which, okay, fine, you can move stuff in that way, but ultimately all new alleles come from mutations. And what we mean by a net mutation is that the forward and the back mutation are equal. So if you have mutation to superhuman strength and high intelligence and ability to use swords and wear bandanas and masks, that's a forward mutation. the back mutation then would be mutation back to your nice eastern box turtle form here. Okay, mutation rates are going to have effects on allele frequencies again. And remember, all microevolution is change in allele frequency. So does that microevolution happen? Yeah, you can measure it really easily out in the field. So all I did here was changed the forward mutation and the back mutation rate, and you can see the effect that that's going to have on the frequency of alleles. This is it's a pretty small population in the grand scheme of things, but it's not so small that you can't get stability. But you can see if you have a mutation rate that's 0.3 forward mutation, the population finds a new steady state here.